started with a signal that should have meant relief. Instead, it meant trouble. Voyager 1 was still calling home. The radio carrier was strong, even the tone was steady. Everything looked normal until engineers tried to read the actual message. Then the nightmare appeared. The numbers made no sense. The oldest spacecraft still speaking to Earth was alive, but it was talking in gibberish, and that meant humanity could lose its only working witness beyond the edge of the solar system. Think about how strange that is. A machine launched in 1977 was still sending something back from more than 15 billion miles away. Yet one tiny failure turned all that distance into pure silence in disguise. The spacecraft had not died. It had become unreadable. And with every passing day, the team on Earth had to ask a terrifying question. If Voyager 1 could no longer tell us what it was seeing, what secrets at the border of our solar system would vanish with it forever? Stay with this story, because what happened next was not just a rescue, it was a warning, and the final part may change how you think about the shield that keeps Earth safe. To understand why this crisis mattered so much, you have to go back to the beginning. Voyager 1 was never supposed to live this long. It launched from Cape Canaveral on September 5th, 1977, just weeks after Voyager 2. The mission took advantage of a rare lineup of the giant planets, a natural arrangement that let engineers use gravity like a slingshot. That meant one spacecraft could visit worlds that had once seemed impossibly far away. The original goal was not eternal exploration. It was a bold but limited tour. Fly past Jupiter, fly past Saturn, take images, measure fields, particles, plasma, and radiation. Then, eventually, fall silent. No one in the 1970s expected these probes to keep working for nearly half a century. They were built for a great adventure, not for immortality. But almost immediately, Voyager 1 started rewriting expectations. In 1979, it raced past Jupiter and showed scientists something astonishing on the moon, Io. Volcanoes were erupting there. Not ancient frozen scars, but active volcanoes blasting material into space. It was the first time humanity had seen volcanic activity beyond Earth. Then, in 1980, Voyager 1 swept past Saturn and sent back breathtaking views of the rings. It also gave scientists a crucial look at Titan, Saturn's largest moon, hidden beneath a thick orange haze. That Titan flyby came with a trade-off. Mission planners bent Voyager 1's path northward, out of the flat plane where most planets orbit. It was the right move for science, but it ended the planetary tour forever. No Uranus, no Neptune, no more close encounters. From that moment on, Voyager 1 was heading into deep darkness toward a destination no spacecraft had ever reached. Then came the crossing that changed everything. On August 25, 2012, Voyager 1 crossed the heliopause. That is the outer boundary of the heliosphere, the giant bubble inflated by the sun. Inside that bubble, the solar wind and the sun's magnetic influence dominate. Outside it, the broader galaxy takes over. Every planet you know, every moon, every asteroid, every comet, and every human life in history has existed inside that solar bubble. Voyager 1 became the first human-made object to move beyond it and sample interstellar space directly. That sounds like a clean moment, like crossing a line on a map. Scientists once imagined it that way too. Many expected a fairly smooth handoff, with particles from the sun fading, while particles from interstellar space slowly replaced them. But the real boundary was stranger. Voyager 1 found evidence that this outer frontier was compressed, disturbed, and active. It was not a quiet border. It was a place where conditions changed sharply, where particle populations shifted fast, and where magnetic behavior refused to match simple models. And then came the hum. Years after the crossing, Voyager 1's plasma wave instrument detected a faint, persistent signal in interstellar space. Not a dramatic blast, not a one-time burst. A steady, narrow-band vibration, subtle but stubborn, present from 2017 onward. Researchers described it as a hum in the plasma, the charged gas spread between the stars. Before that, scientists mostly estimated interstellar plasma density using occasional shock waves triggered by solar eruptions. A big solar event would ripple outward, disturb the plasma around Voyager, and give researchers a brief reading. That method worked, but only in flashes. It was like trying to understand an ocean by watching it only when lightning struck. The persistent hum changed the game. Now Voyager was not just waiting for rare solar storms. It was sensing a constant background signature in the interstellar medium itself. That meant scientists could track density more continuously and start seeing that the space between stars is not empty in the way many people imagine. It has texture, it has structure, it has slow-moving weather of its own. Here is where the story begins to feel less like old space history and more like a live mystery happening right now. Scientists still debate the exact cause of that hum. One explanation points to natural plasma oscillations, tiny vibrations in charged particles. Another involves a closely related effect, sometimes called quasi-thermal noise. In simple terms, the particles may be jostling in a way that reveals their density and temperature. Either way, The message is the same. The region beyond the sun's protective bubble is not silent. It is active, measurable, and still not fully understood. And that raises a much bigger question. If the space just outside our solar shield is more dynamic than expected, what does that say about the shield itself? The heliosphere matters because it protects us. It deflects a large share of high-energy cosmic rays, particles accelerated by violent events such as exploding stars. According to Voyager results, that shield helps block more than 70% of this radiation. Earth is not drifting naked through the galaxy. We live inside a bubble shaped by the sun, and that bubble reduces part of the constant particle storm around us. But what if the wall is more complex than we thought? Voyager 1 suggested exactly that. Data from the boundary implied compression around the heliopause. Later, Voyager 2 helped confirm that the zone beyond the heliosphere is not some smooth, untouched emptiness. Voyager 2 crossed into interstellar space on November 5, 2018, from a different direction. Its readings showed dramatic particle changes, just as Voyager 1 had seen. And perhaps most surprising of all, Voyager 2 supported a strange magnetic result first hinted at by Voyager 1. Scientists had expected the magnetic field outside the heliosphere to differ more clearly from the one inside. Instead, the field directions on both sides appeared unexpectedly aligned. That did not mean they were identical, but it did mean the boundary was behaving in a more connected, more puzzling way than many models predicted. The hull of our solar bubble, as some scientists described it, might be a little leaky. Particles could slip through. Magnetic behavior could remain linked across the border. The sun's domain and the galaxy beyond it were not cleanly separated worlds. Pause on that for a second. The edge of our solar system may act less like a hard shell and more like a living frontier, a breathing, shifting magnetized contact zone between our star and the Milky Way around it. And Voyager 1, a machine older than most laptops' inventors, is the outpost telling us that from the outside. If you were the engineer receiving those signals, would you even believe it at first? That is part of what makes the next chapter so intense. In late 2023, the very spacecraft carrying this priceless information began to fail in a way that threatened the mission at its core. On November 14th, Voyager 1 stopped sending readable science and engineering data. Mission controllers could still detect the signal. They knew the probe was there, but the data stream had collapsed into unusable output. Imagine hearing a voice through a wall and realizing every word has been scrambled. This was not a small annoyance. Voyager 1 is so far away that radio commands take about 22.5 hours to reach it, and another 22.5 hours for a response to come back. One question and one answer can consume almost 2 full days. Troubleshooting becomes an exercise in patience so extreme it barely feels human. You send an instruction, then you wait through a day of silence. Then, if you are lucky, you get one clue. For 5 months, that was the rhythm. The spacecraft kept sending back nonsense. Engineers at NASA's Jet Propulsion Laboratory had to diagnose a living machine they could not touch, could not see directly, and could not interrogate in real time. Every test had to be careful. Every guess had to count. Because Voyager 1 was not just old, it was aging on borrowed power, with systems that had already survived far longer than anyone thought possible. Eventually, the team traced the problem to the flight data subsystem, the hardware that packages scientific and engineering information for transmission. A single damaged memory chip had corrupted part of the code stored there. Roughly 3% of the FDS memory was affected, but that was enough to break the outgoing data stream. One tiny wound inside a machine billions of miles away had turned the most distant scientific outpost in history into a speaker without a language. There was no repair mission. There never could be. No astronaut was coming, no robotic mechanic was waiting nearby. So the team attempted something extraordinary. They rewrote the way Voyager 1 used its own memory. Essential sections of code were divided up, moved into different storage locations, and adjusted so the whole system could still function even though one part of the old memory space had effectively become unusable. That is easy to say in one sentence. It is much harder to appreciate what it meant. Engineers were patching 1970s software architecture on a spacecraft in interstellar space. They had to identify which code mattered most, relocate it, update references to the new memory locations, and trust that commands sent across more than 24 billion kilometers would land exactly as intended. No instant feedback, no second-by-second monitoring. Just deep focus, decades of accumulated knowledge, and a willingness to perform remote surgery across a gulf that light itself needed nearly a day to cross. The first major win came in April 2024. Engineers moved the code responsible for packaging engineering data, then waited for the answer to crawl back from the darkness. On April 20th, readable engineering data returned. For the first time in months, the team could once again see the health and status of the spacecraft. It was a breakthrough, but not the end. Engineering data told them Voyager was speaking more clearly. Science data still had to come back too. Then it did. Weeks later, the full science stream returned, restoring access to the information Voyager 1 was collecting in interstellar space. The hum was still there. The plasma readings continued. The magnetic field data kept arriving. Humanity had not lost its farthest scout after all. And if this story stopped there, it would already be one of the greatest repair efforts in the history of engineering. But here's the part almost nobody is prepared for. Saving Voyager 1 did not simply preserve an old mission. It preserved our only direct report from a region that still seems to be defying expectations. The heliopause is not merely a textbook border. Observations from the Voyagers suggest a disturbed transition zone, compressed plasma, shifting particles, and magnetic alignment across the boundary that surprised scientists. The interstellar medium just beyond is denser than the plasma inside the heliosphere, as expected, but the detailed behavior around that frontier has been anything but simple. Some descriptions on the internet call it a wall of fire. That phrase is dramatic, and it can mislead if taken literally. Voyager did not fly through flames. There is no oxygen fire burning at the edge of the solar system. But the phrase survives because the particle energies and temperatures associated with that region can sound shocking. Even so, scientists are talking about plasma behavior and particle motion, not a burning wall in the ordinary sense. The reality is less cinematic, but in some ways even stranger. A near vacuum can still host particles with tremendous energy. A sparse region can still be violent in the way physics measures violence. That matters because the heliosphere is our shield. It is shaped by the solar wind, pressed on by interstellar space, and changed by the sun's activity over time. Voyager 1 and Voyager 2 crossed the boundary at different places and at different points in the solar cycle. That alone showed scientists that the heliopause moves. It expands and contracts as the sun breathes through its roughly 11-year rhythm. So there is no single frozen edge. There is a flexible frontier, reacting both to the star at its center and the galaxy around it. Now imagine future human missions going farther from the sun than ever before. Imagine probes built to operate for centuries. Imagine attempts, one day, to send machines toward another star. Suddenly, the behavior of this boundary is no longer a poetic detail. It becomes a practical one. How much radiation does the heliosphere really block? How porous is it? How does particle density change near the crossing? What kind of instruments survive there? Voyager is helping answer those questions with real data instead of guesses, and the timing could not be more urgent. Because even after the 2024 recovery, Voyager 1 remained in a race against its own fading power supply. The spacecraft runs on radioisotope thermoelectric generators. These devices convert heat from decaying plutonium into electricity. That electricity slowly declines year after year. NASA says each Voyager loses about 4 watts annually. 4 watts may not sound like much on Earth, but on a craft living so close to the edge of survival, it is everything. Every lost watt becomes a decision. Do you switch off a heater? Do you disable an instrument? Do you risk letting a component run colder than it was designed to handle? Some parts of Voyager have already survived in conditions their builders never expected. That alone feels almost unreal. The spacecraft is still working in temperatures and circumstances that would have seemed impossible back when disco was on the radio and personal computers barely existed. In 2025 and 2026, NASA began making deeper sacrifices to keep the mission alive. One instrument was turned off on Voyager 2 in 2025. Then, on April 17, 2026, engineers sent commands to shut down Voyager 1's low-energy charged particles experiment, known as LECP, to conserve power. Kareem Badruddin, Voyager mission manager at JPL, said plainly that turning off a science instrument was not anybody's preference, but it was the best option available. That sentence carries a quiet sadness. It is the sound of caretakers keeping a legend alive one sacrifice at a time. After that shutdown, Voyager 1 still had 2 operating science instruments that mattered enormously to this mystery. One listens to plasma waves, the other measures magnetic fields. Those are the very tools that keep revealing the strange behavior beyond the heliosphere. In other words, the spacecraft is shrinking down to the bare essentials required to continue its most important discovery. And NASA is not done trying. The mission team has been working on a more ambitious energy-saving strategy, nicknamed the Big Bang. The idea is to switch off certain powered devices and replace them with lower power alternatives in a coordinated move, extending the lives of both Voyagers. It is an astonishing image if you think about it long enough. Human beings on Earth are still redesigning the energy behavior of machines launched nearly 50 years ago, and they are doing it across billions of kilometers with day-long signal delays. There's even another milestone approaching. NASA's own mission status page says Voyager 1 is expected to become one light day from Earth in November 2026. That means its radio signal will take a full 24 hours to arrive. Not almost a day, a full day. No active spacecraft in history has ever operated that far away while still sending usable data home. When that moment arrives, every conversation with Voyager will become even more ghostly. A command leaves Earth, crosses an ocean of black for an entire day, and only then reaches the craft. What would it feel like to work that mission? You would wake up each morning knowing the spacecraft you care for is older than most of your coworkers, farther away than any object humans have ever operated, and one failure away from permanent silence. You would know that every small success carries the weight of human curiosity itself. Because when Voyager sends data, it is not just reporting on itself. It is answering a question our species has asked for generations. What is it really like at the edge of home? The answer, so far, is not what we expected. Interstellar space near the heliopause is not just empty calm. It is structured. It is denser than the plasma inside the heliosphere. It contains cosmic rays from beyond our solar system. It carries a persistent plasma hum, and the boundary itself appears compressed, disturbed, and magnetically surprising. Instead of a simple shell, we may be looking at a dynamic interface where the sun and the galaxy negotiate constantly. That changes the emotional meaning of Voyager 1 too. This is not only a survivor from the past, it is a current observer of something no telescope near Earth can directly sample. Every observatory on or near our planet studies the universe from inside the heliosphere. Every model of the interstellar medium once had to infer conditions beyond that boundary from the inside, looking out. Voyager crossed the line. It became the only direct reporter stationed on the other side. And it is doing that with less processing power than devices we now treat as toys. That contrast is almost hard to absorb. The spacecraft belongs to an era before the internet, before smartphones, before digital life as we know it. Yet it is still measuring plasma waves and magnetic fields beyond the sun's influence. It is still reshaping scientific assumptions. It is still doing first-of-their-kind science while modern civilization streams videos, launches apps, and forgets how extraordinary patient engineering can be. Scientists are still arguing over what exactly Voyager is hearing out there, and that debate is one of the most exciting parts of the whole mission. In science, the biggest breakthroughs often begin with an annoyance, a reading that refuses to fit the old picture. The persistent signal beyond the heliopause is like that. It is faint, narrow, and easy to miss if you are expecting something loud, but quiet data can be the most dangerous data of all, because it forces researchers to rethink assumptions they stopped questioning years ago. Some experts see the hum as a natural plasma oscillation, the kind of vibration charged particles can make when they settle into a surrounding electric environment. Others think the signal may be better explained by a related process that could reveal temperature and density in a more subtle way. To most people, that sounds like a small technical disagreement. It is not. If scientists can pin down the source of the signal with confidence, they can turn Voyager 1 into a far more precise probe of interstellar space than anyone expected when it launched. That would mean the spacecraft is not only surviving in an alien region, it is teaching us how to measure that region better than we knew how to measure it before. There are other open questions too. How stable is the plasma density around Voyager over long stretches of time? Does the hum change slowly as the spacecraft moves through slightly different regions of the interstellar medium? Are there hidden waves, weak shifts, or patterns buried inside the signal that only become clear after years of patient analysis? And perhaps most important, how much of what Voyager is seeing reflects the wider galaxy, and how much reflects a disturbed zone still shaped by the sun? That last question matters because both Voyager spacecraft appear to be in a transitional region just beyond the heliosphere, not in some perfectly calm, untouched sea. In other words, humanity may still be standing just outside the front door, not deep in the neighborhood. Even there, the physics is already surprising. That should make you wonder what lies farther out, where no instrument from Earth has ever gone. This is why scientists treat every additional month of Voyager data like treasure. The mission is no longer just about distance records. It is about time series. That means watching how conditions evolve, not simply grabbing one dramatic crossing and moving on. A single snapshot can be famous. A long record can change theory. Voyager 1 is giving researchers the rare chance to see whether the space beyond the heliopause flickers, settles, thickens, thins, or shifts in ways that only reveal themselves across years. And there is something else almost poetic hiding in that idea. The farther Voyager travels, the more valuable each measurement becomes, because every new mile places the spacecraft in a region no human-made object has ever sampled before. Even a tiny change in density, a subtle bend in magnetic direction, or a small change in particle behavior could represent first contact with conditions no one has ever measured directly. The mission keeps moving into new science simply by staying alive. That is why the rescue in 2024 felt bigger than a technical repair. It felt like saving a conversation we're not ready to lose. Not because Voyager will answer every question, but because it is the only witness already standing where the next questions live. Once it goes silent, the flow of first-hand interstellar measurements from that location ends immediately. Future missions may follow one day, but not soon. No replacement is cruising behind it. No second backup spacecraft is waiting to take over. So the true tension in this story is not just whether Voyager survives another year. It It is whether humanity can keep listening long enough to understand what it has already begun to hear. The hum is still there, the magnetic mystery is still there, the shifting frontier around the heliosphere is still there, and somewhere inside that slow whisper from interstellar space may be the clue that finally tells us whether our solar system's protective bubble is a shield, a filter, a sieve, or all three at once. Maybe the deepest reason Voyager 1 matters is this. It turns the universe from a picture into a place. Telescopes can show you light. Equations can show you possibility. But only a traveler can tell you what the wind feels like when you arrive. Voyager is that traveler. It crossed the border, looked back without eyes, and told us the frontier around our home is stranger, louder, and more alive than we ever dared to imagine. And we are still listening while we can. If you have made it this far, ask yourself something. What discovery would make all these years worth it? Would it be finding that the heliosphere shields Earth more strongly than we thought? Or would it be learning that the boundary is more fragile, more connected to the wider galaxy, and more vulnerable to outside pressure than our old models suggested? Because both possibilities matter. If the heliosphere is stronger than assumed, that helps us understand how life on Earth has been buffered from radiation over deep time. If it is more permeable or more turbulent than expected, that matters too. It affects how scientists think about cosmic ray exposure, about long-term spaceflight, and about what any future mission might face when leaving the sun's protective domain. Voyager 1 is not solving all of that alone, but it is giving us the ground truth we lacked. And there is a deeply human side to this mission that numbers alone cannot capture. The people now keeping Voyager alive are, in many cases, younger than the spacecraft. Some were not born when it crossed Saturn. Some were not born when it entered interstellar space. Yet they inherited responsibility for a machine that still carries the ambition of an earlier generation. They are not just maintaining hardware. They are tending a bridge between eras of human thought. One end of that bridge is the world of slide rules, analog engineering instincts, and missions planned by people who dared to think on a solar system scale. The other end is our world, where the same machine still whispers to us from the dark and forces us to confront how little we truly know about the space just beyond our cosmic doorstep. And then there is the Golden Record. Bolted to Voyager 1's side is one of the most poetic artifacts humanity has ever launched. A gold-plated copper record carries greetings in dozens of human languages, natural sounds from Earth, music from different cultures, and encoded images meant to introduce our world to any distant finder. It even includes symbolic instructions showing how the record should be played and where it came from. The odds of anyone ever finding it are almost impossibly small. But that was never really the point. The point was to send a trace of ourselves into the deep future. Long after Voyager stops transmitting, long after its instruments go dark, the spacecraft will keep moving. It may drift for millions or even billions of years. It will pass through the galaxy carrying a heartbeat of human civilization. The science data will end, but the object will remain, silent and still faithful to the direction we gave it. That is beautiful. It is also heartbreaking. Because right now, this is the narrow window when Voyager 1 is still both artifact and witness. It is not just carrying our message. It is still sending one back. A faint radio whisper from beyond the heliosphere is telling us that the boundary around our solar system is alive with physics we did not fully predict. It is telling us that interstellar plasma can hum. It is telling us that magnetic fields may stay connected across a frontier we once imagined as cleanly divided. And it is telling us all of that while dying slowly. At some point, no fix will be enough. Not the memory patch, not the careful shutdowns, not the Big Bang power strategy. Physics always wins in the end. The generators will weaken, more instruments will go dark. One day, the last working transmitter will fall silent, and the final signal will start its one-day journey back to Earth. Imagine that last message. No one will hear it instantly. No one will know, in the moment it leaves the spacecraft, that it is the last. It will cross the black alone. Then, a day later, on a planet still turning beneath clouds and oceans, antennas will catch the fading arrival of a voice that has been traveling since before dawn the day before. Somewhere, a screen will update. Somewhere, an engineer will understand. And in that small, quiet room, humanity's most distant explorer will become history. But not yet. For now, Voyager 1 is still out there. It is still moving through interstellar space. It is still listening to plasma waves. It is still measuring magnetic fields. It is still helping scientists map the true nature of the border that surrounds our solar system. And every bit of that data matters, because there is no backup observer waiting beside it. That is why this story feels larger than one aging spacecraft. It is about the shape of home. It is about the invisible shield wrapped around every life on Earth. It is about the line between our star and the galaxy beyond. And it is about how human beings, with old hardware and unreasonable persistence, managed to place a sensor on the far side of that line and keep it talking for almost 50 years. Maybe that is the real shock in all of this. Not just that Voyager 1 found a hum in interstellar space, not just that the heliopause turned out to be stranger than expected, not just that engineers rescued a broken spacecraft from billions of miles away. It is that all these things are happening in the same story at the same time through a machine that should have gone silent generations ago. We used to think the edge of the solar system was the end of the familiar. Voyager 1 revealed that it is also the beginning of a new kind of mystery, a place where the sun's protection weakens, where the galaxy presses in, and where the quiet between the stars is not quiet at all. So when the next faint signal arrives from the deep space network, it is carrying more than data. It is carrying time. It is carrying proof that curiosity can outlive expectation. It is carrying evidence that the universe still becomes stranger the closer we look. And it is carrying one unresolved question that may define Voyager's final years. What else is waiting in that hum before the last instrument goes dark? If you want more stories like this, stay close to Galaxy Sphere, because the next mystery may already be on its way to Earth. And when you think about Voyager 1 tonight, ask yourself this. If our oldest explorer is still finding surprises at the edge of home, what do you think the rest of the galaxy is still hiding from us?